In this video, we're going to explore something called the Cayley-Hamilton theorem, which is a really powerful result which we're going to use to find inverses really cleverly. So take a standard 2 by 2 matrix like this. We've learned that there's this equation called the characteristic equation, which is simply the determinant of your matrix minus lambda times the identity. And we use the characteristic equation to find eigenvalues. Now, we know that if we set that equal to 0, that the resulting values of lambda will be the eigenvalue. So let's just multiply this out and let's explore this characteristic equation a little bit. So in this case, it's that minus 10 equals 0. Expanded gives us lambda squared minus 5 lambda plus 4 minus 10 is minus 6 equals 0. All right, now let's dig into this. Suppose that we applied this is a number, right? Lambda squared minus 5 lambda minus 6. We multiplied an eigenvector of the matrix by this. So this is simply multiplying a vector by a number. So take this number and multiply it by some eigenvector. And of course, it's still going to be 0, just with a 0 vector, so like 0, 0. We can expand this out, and that's lambda squared times e minus 5 times lambda e minus 6e, and that'll still be 0. But remember, by definition, since lambda is the eigenvalue of this matrix, we know that m of e is the same as lambda e. And similarly, if you apply the matrix twice, m squared to e, you get lambda squared e. Now, that tells me that that lambda squared e can be replaced with m squared of e. That will do the same thing. And that lambda e can be replaced with me, so that's 5 5e, 5me, 5m of e. And then 6e is the same as 6 times the identity of e. And since matrices are also distributive, I can now pull out m squared minus 5m minus 6 times the identity of e, and that should still be 0. Okay, now here's the interesting part. What does this mean? This means we've got this matrix here, which when applied to E gives us 0. Now, this is a matrix, and matrices can sort of crush lots of different vectors down to 0, and doesn't really prove anything about that matrix. However, it does this to both of the eigenvectors of this matrix. Now, I don't even know what the eigenvectors of that matrix are, but the point is they're two independent vectors, meaning maybe one of them is like that and another one is like that. Now, they're probably not there, but just the point is they're two vectors pointing in different directions. Now, the issue is if this matrix crushes this one back to 0 and this one back to 0, it must crush everything back to 0. And the reason for that is if you pick any point in 2D space, you can get there using some combination of these two vectors. Because the vectors are not pointing in the same direction, there is some way to combine these to get anywhere. Just as a little example of that, how do we get here, for instance? Well, you could do this one, and then this one, that's the other one there, and then maybe this one again, and then maybe only half, maybe only about 2/3 of that one, and then maybe one of those ones, and then maybe a little bit more of those. So some combination of those, however messy it is, you can get anywhere. It's basically, in use technical language, we can span 2D space using our two eigenvectors. The fact that this matrix crushes both eigenvectors means it crushes all of 2D space. And there's only one matrix which crushes all of 2D space, and that is the 0 matrix. Zeros everywhere. So this tells me that m squared minus 5m minus 6i is 0. And by 0, I mean the zero matrix. 0 is everywhere. So this is the Cayley-Hamilton theorem. The Cayley-Hamilton theorem says that if you take your characteristic equation, which is your equation formed to find eigenvectors or eigenvalues, that if you just replace your lambda with m itself, you will get the zero matrix. Now, that's a bit counterintuitive, and also we don't yet know why that's useful. I'll come on to that in a moment, but let's just check that out. So in this case, what is that? Well, it's m squared, which is 4251 squared, so 4251, minus 5 times m, so minus 5 lots of 4251, minus 6 times the identity, which is 1001, is apparently 0. Let's see. So this one we get 16 plus 10 is 26. Then 8 plus 2 is 10. 20 plus 5 is 25. And 10 plus 1 is 11. Then 5 lots of this. So that's 20, 10, 25, and 5. And then minus 6006. 26 minus 20 minus 6 is 0. 10 minus 10 minus 0 is 0. 25 minus 25 minus 0 is 0. And 11 minus 5 minus 6 is 0. So there it is. So this is true for all matrices. If you have when you form your characteristic equation, if you just replace your lambda with the matrix M and you replace your number with that number times the identity, that will also be 0. Okay, so that's the Cayley-Hamilton theorem. In the next video, I'm going to show you how you can use the Cayley-Hamilton theorem to find inverses in a really clever way. So see you there.